Hello students, today let us solve a problem on P chart. So here they have given a question. So there is a table which shows the collected data in the manufacturing unit. So they are asking us to compute the trail control limits for P chart as well as to draw the P chart, that is the fraction defective chart. So first of all, we have to calculate the P value for each sample. So they have given us the subgroup, that is the sample number, and the number they have inspected, that is the sample size, which is 300 for all the samples, and then they have given us the number defective, that is P value. So for the solution, first thing we have to do is calculation of fraction defective of each sample. Small p value is equals to np divided by n. So here this is np, that is the number defective. This is not p, this is np, and this is n, that is the sample size. So for the first sample, sample 1, n is equal to 300 and np is equal to 12, which they have already given. So the value of p is equals to 12 divided by 300. So that will give us 0.040 as the answer. For the first sample, the fraction defective value is 0.04. Now for sample number 2, n is equal to 300 and np value is 3. So p value will be 3 divided by 300. So that will give us 0.010. For sample number 3, n is equal to 300 and np is equal to 9. So p value is equal to 9 divided by 300, which will give us 0.030 as the p value. Similarly, for the sample number 4, n is equal to 300 and np is equal to 4, that is p is equals to 4 divided by 300, which will give us 0.013 as the answer. For sample number 5, n is equal to 300 and np is equal to 0. So p is equals to 0 divided by 300, which will give us 0. So in the same way, for all the 25 samples, we will calculate the fraction defective, that is the p value. So here for the first sample, the answer or the fraction defective value was 0.040. For the second, it was 0.010. For the third, it was 0.030. For the fourth one, it was 0.013. For the fifth one, it was 0. For 6, 0.020. In the same way, we will calculate for all the 25 samples. So I am writing down the values of all the samples which are being calculated. This is 30 and this one is 0.010, and next we have 0, then 0.017, then we have 0.023, and then we have 0.027, 0.053, 0.007, 0.017, 0.020, then this is 0, then 0.010, the last one is 0.007. So with this same formula, that is NP divided by N, that is number defective divided by the size of the sample, we will calculate all the fraction defective values. The next step is calculation of average fraction defective. So that is P dash is equals to sigma of P divided by M, or sigma of NP divided by sigma of N. So this is N. So sigma, that is 300, we have to add 25 times, which will give us sigma of N is equals to 7500, and then sigma of NP, so this is NP, sigma of NP is 138. When we add up all these values, 12 plus 3 plus 9 plus 4 plus 0, we will get all till 25, we will get 138 as the answer. So P dash is equals to 138 divided by 7500. So P dash value is 0.018. So this is the average fraction defective. Now the next step is calculation of the control limits. So upper control limit for P chart is P dash plus 3 into root of P dash into 1 minus P dash divided by N. So we have found the upper control limit value. So we will write it as 0.018 plus 3 into root of 0.018 into 1 minus 0.018 divided by 300. So for this, we will get the upper control limit as 0.041 after simplification. So this is the upper control limit. Now calculation of lower control limit for the P chart, that is P dash minus 3 into root of P dash into 1 minus P dash divided by N. So 0.018 minus 3 into root of 0.018 into 1 minus 0.018 divided by 300. So the lower control limit for P value is minus 0.005. So there is no meaning in negative defective. Hence, we will take this as 0. That is the lower control limit, we will take it as 0. I will write it down. No meaning in negative defective. So we will take lower control limit for P chart as 0. So let us take 0, 0 as the answer. The next step is plotting of the chart. So here we are taking the P values on the y-axis and the number which is inspected, that is the subgroup number, on the x-axis. Now, as we have already obtained the p-values for each and every sample, we will plot it on the graph. So for sample number 1, the p-value is 0.04. So I have marked it here. Then for the second sample, it is 0.01. So I have marked it here. For the third sample, the p-value is 0.03. For fourth value, it is 0.013. So it is somewhere here. So likewise, we will check all the fraction defective values, that is the p values, and we will mark it along the corresponding sample number. So I have marked all the values, and then we will join these with the help of straight lines, as I have already done here. Now, before we stop it, we will check for the upper control limit and the lower control limit. We will mark the upper control limit and lower control limit. We have already seen that the lower control limit was a negative value, that is why we have taken it as 0. So this is the lower control limit, that is 0. Now the upper control limit is 0.041. So it will come somewhere here. So this is upper control limit, that is 0.041. Okay. So now after seeing the graph, we can say that, so this must be somewhere, this must be marked here. So after seeing the graph which we have plotted, we can say that this graph has point above the control limit. So at point 19, we see that the p-value is 0.053, which is more than the upper control limit. So we can say that this graph or this process is out of statistical control, and there are assignable causes present in this process. So hence, from the graph, we find that there is a value of p above the upper control limit of p chart, and hence it shows that there are assignable causes variation in the process, and that is why we conclude that the process is not under statistical control and requires homogenization of the p-values p19, that is 0.053, for revised process average or fraction defective, average fraction defective, and control limits. So this is all about the p chart problem. I hope you have understood the problem. Thank you.